Nanoparticles often exhibit different characteristics from the bulk form of the element because of their size and greater surface area to volume ratio. Colour changes at the nanoscale directly relate to the size of the nanoparticle, a characteristic that is particularly evident in the synthesis of gold nanoparticles. This experiment aims first to make gold nanoparticles in solution. We call this colloidal gold. Then to demonstrate how a laser beam is used to test for their presence. And finally, to demonstrate how increasing the size of the nanoparticle changes its colour. The solutions and equipment are 20 ml of gold hydrogen tetrachloride solution, 2 ml of sodium citrate solution, 1 ml of sodium chloride solution, distilled water, magnetic stirrer and hot plate combination. A nanoparticle has a diameter of 10 to 100 nanometers and is made up of a cluster of atoms. Now let's make some nanoparticles. We'll start by adding 20 ml of the gold solution to the conical flask. We'll heat this solution until it boils, which usually takes 4 to 5 minutes. We will just keep it stirring to ensure it heats evenly. Please note the watch glass on top of the conical flask. It's there to prevent the solution evaporating as it heats. Once it boils, we'll remove the watch glass and add the citrate solution. Okay, it's boiling. Leave the stirrer on and add 2 ml of sodium citrate, which facilitates a chemical reaction and produces uniformly sized particles. Now we turn off the heat. You can see the colour change. It's gone from light gold through a blue colour phase. As we continue stirring, you can see the colour change again to bright red. The red colour indicates that we have produced nano-sized gold particles of around 10 to 20 nanometers in diameter, or colloidal gold. That is, gold nanoparticles suspended in solution. This is the chemical equation for the redox reaction, where gold ions react with citrate ions to form gold atoms. As well as acting as a reducing agent in producing the gold atoms, citrate ions act as a shielding agent wrapping around the cluster of atoms which constitute the nanoparticles. This creates an electrostatic sheath around each nanoparticle, which prevents agglomeration and stabilizes the particles in solution. How do we know the nanoparticles are present? Let's look at the prepared nano-gold solution. First, remove the red solution from the stirrer. Allow it to cool, and then transfer some of this solution into a test tube. Pour distilled water and gold chloride solution into 2 other test tubes. So, our solutions are distilled water on the left, gold solution, our original solution, nanoparticles of gold on the right. We now shine a red laser beam through each of the test tubes to find out which, if any, contains gold nanoparticles. Remember, gold nanoparticles are a colloid. We can't see them, but we can usually detect them by the way they react to light. If we shine this beam through the test tube with distilled water, you'll see its entry and exit points, that's all. There is no visible passage of light. If we shine it through the original gold chloride solution, we get the same result. No passage of light. It's just a bright spot on either side. Now we'll shine our red laser through the test tube we hope has the gold nanoparticles. What you see now is the passage of light as a red beam from one side of the test tube to the other. The suspended nanoparticles are reflecting and scattering the light as it passes through the solution, a response known as the Tyndall effect. We have indeed produced gold nanoparticles and have just confirmed their presence. We will now increase the size of the nanoparticles and observe how that impacts on their colour. Here in the test tube holder are 2 samples of the particles we've just produced. We will add to one of the test tubes a few drops of sodium chloride solution, shake it and observe the results. What we now see is a darker solution in the left-hand test tube. By adding sodium chloride to the original gold nanoparticles, we've caused the particles to increase in size, which affects the way they reflect light and therefore changes their observed colour. Adding sodium chloride disturbs the electrostatic sheath around each nanoparticle, resulting in positive attraction between nanoparticles, agglomeration, and therefore particles larger than 20 nanometers. So we have not only created gold nanoparticles, we have created nanoparticles of different sizes and observed how their size determines their colour. That concludes our experiment. We have shown how to produce gold nanoparticles, how to confirm their presence, and how to exploit some of their behaviours.